Welcome, everyone. And I'm really pleased to welcome you again to our Friday webinar. It's the 1st of December. The years just rushed by, and it's all about the sun today. I'm really pleased to introduce to you Ivey Davis, who is a graduate student at Caltech. Now, Ivey has a very interesting history. So Ivey, come on board and I can introduce you. Very nice to see you. She's amazing because she's not only very scientifically gifted, she also is an artist. So Ivey, that's incredible. You're very talented and we're really pleased to welcome you. We're going to hear all about stellar evolution and lifetime. So it's all yours. Welcome.
Yeah, thank you so much for having me. I'm super excited, and it's super great to see so many people from all over. So yeah, thank you for having me, and thank you everybody for coming. I guess I can go ahead and share my screen then.
That's right. I'll go on science and just tell me when you want to launch the poll and so on. Okay, so.
Okay, great. Will do. Okay. Can everybody see this okay? Okay, great. Cool. So yeah, as Christian said, my name is Ivey and I am a grad student at Caltech. I'm in my 4th year now. And as Christian mentioned as well, and as you might be able to guess from the title of my talk, the work that I do is focused on understanding the behavior of the sun when it was much younger than it is today, when it was about 100 million years old, as opposed to its current age of about 5 billion years old. And I was really excited to give this talk, to be invited to give this talk by iTelescope, because the first 3 years of my time at Caltech was actually dedicated to developing the instrumentation for doing my science. And so I was scrolling through the iTelescope website, looking at the different telescopes they have available, and I saw that a lot of them were these plane wave telescopes, in particular these CDK or Corrected-Dahl-Kirkham telescopes that are 20-inch apertures. So you might hear me calling them CDK 20s. In particular, there is the T31, which is a plane wave CDK 20, which was really exciting to see because the telescope that I use for my science is also a plane wave CDK 20 on a different mount, and also it has a nice cover on it to prevent dust from falling in, but it's the same optical tube. And so because this is a webinar for iTelescope, and also because I feel like astronomers have a tendency to take instrumentation for granted, I wanted to take a few minutes to talk about the sort of decisions that go into designing the instruments that we use for science. In order to do that, actually, first, this is a different perspective of my telescope called flarescope. In this view, you can see the dome of the Hale telescope on Palomar. My telescope flarescope is installed on Palomar Mountain. Okay, now into the design decisions. So these are the specs for the T31 hosted by iTelescope, as posted on the iTelescope website. I'm not going to go through all the details because there's quite a bit here, but there's a few things I wanted to point out. The first is what camera is being used. So this is a Finger Lake instrument, or an FLI camera. Finger Lake Instruments actually has a lot of different astronomical equipment. The filter wheel that I use is actually from Finger Lakes. They're a great company. And this detector has a quantum efficiency that's at QE. So its quantum efficiency, which all quantum efficiency refers to, is how effective the camera is at taking photons and converting them into electrons. So how good it is at actually converting the light into a signal that we can read out. So its quantum efficiency is around 70%, which is really decent. I am hypothesizing, though, that it's not higher than 70% because it is what's called a front-lit sensor. So basically all that means is that the light has to go through more material in order to actually reach the electronics. And when it has to go through more material, then it has more opportunities to be scattered and absorbed. So the quantum efficiency is going to be a bit lower because of that. On the other hand, the camera that I use for my observatory is an Andor Ixon 3888, which is actually a discontinued model, but there are other Andor cameras that are very similar. There's the Andor Ixon Ultra now. And this detector is backlit, which means it has less material it has to go through, and so its quantum efficiency is much higher, as much as 95% in some of the wavelengths that I'm interested in doing my science in. And quantum efficiency for me was really important because I need really high precision photometry. So maximizing the quantum efficiency was important for me. It's not necessarily necessary for astrophotography, where you might be looking at brighter objects, or you just don't need that level of precision. Now, next up, a little bit about the pixels. The pixel size on the FLI, on the T31's camera is about 12 microns. That's pretty standard for these telescopes. And when combined with the optics of the telescope, then you get a resolution of about 1 arcsecond per pixel, which for folks who aren't used to working in arcseconds, that's 1/60th of an arc minute, which is in turn 1/60th of a degree. So this is about 1/3600th of a degree in size, so pretty small. On the other hand, for my telescope, my camera, the pixel size is about the same, about 13 microns, but my resolution is smaller, 0.7 arcseconds per pixel, which confused me at first because nominally these are the same optical tubes, the same telescope, so you should expect for the same pixel size, you would have the same resolution. But as it turns out, this telescope has something that's called a focal reducer installed. And focal reducer does, as the name implies, it reduces the focal distance. And so when you do that, you can get a larger resolution scale. And this is really important if you want to take really large field of view images, which is pretty common for astrophotography. You don't want to have to take tiled images of all those pretty nebula. I'm only interested in individual stars, so I don't need a big field of view. But speaking of field of view, the T31's camera is about 9 megapixels, so quite a few pixels. And with that number of pixels combined with its resolution, that gives it a field of view of 56 by 56 arc minutes. So basically 1 by 1 degree, which is huge by astronomical standards. On the flip side, my array is only 1 megapixel, and so its field of view is only about 12 by 12 arc minutes. So about 1/5 of the size of the field of view, or the dimensions of the field of view in any direction, or about 1/25th of the area. And to give you a sense of what that actually looks like, this is a picture from the iTelescope website again. So this is the Orion Nebula, and this white box around it represents the field of view of the T31 hosted by iTelescope. And then this little red box represents the field of view of my telescope. So much smaller, but the trade-off is that I have really high precision. And I sort of want to emphasize that there's no such thing as the best telescope. We throw around words like the best telescope, but like, for instance, this is the field of view of James Webb. So quite small, but its precision is extremely high. I don't think anyone would doubt the quality of the data products of JWST. And then on the completely opposite end of the spectrum, there's the Vera Rubin Observatory with its massive 3.5 by 3.5 degree field of view. And it has such a large field of view because it's a survey telescope. It wants to be observing as much of the sky as frequently as possible, so it needs that large field of view. So this is me going on my little rant of what it means to be a good telescope. I don't think there's such a thing as the best telescope. I think there's just the best telescope for what you want to do. So with all that said, now I'll hop into the science, the meat of the talk. So I'm going to start with a discussion of space weather on the sun as a way to introduce what space weather is exactly. And then I'll talk a little bit about what we understand of space weather on other stars, in particular, how we study space weather in visible light as well as in radio light, because those are the two parts of the spectrum that mean the most to me. And then from that, we can talk a little bit about what we're learning from these stars, what they can tell us about how our sun was behaving when it was younger, and then really briefly what the future of studying space weather looks like. So to start with talking about space weather on the sun, I always like to give this little history lesson. So even though we've known about the sun for quite a long time, solar flares were only first observed in 1859. This is what's called the Carrington event. It was observed by Richard Carrington as well as Richard Hodgson in 1859. This drawing on the right is the drawing done by Carrington following the event. And this was a really cool event, not just because it was the first time it had ever been observed, but also because in the following days, there were really extreme electromagnetic phenomena occurring at the Earth. And by extreme, I mean that aurora were observable down to latitudes as low as 20 degrees. So folks in Texas, folks in Puerto Rico were able to see these aurora, which I say is cool, but I can imagine it was probably terrifying for folks at the time who had never seen an aurora, maybe had no idea they were even a thing. In addition to the aurora, telegraph stations were actually catching fire because the current passing through them was so extreme. And actually, the telegraph stations catching fire is how folks were able to confirm for the first time that the aurora were electronic in nature. Because the telegraph stations were catching fire, that implied there was a bunch of charged particles impinging upon them. And because that was happening at the same time that all this auroral activity was occurring, they're able to confirm that aurora are caused by charged particles. And because this is following the flare event that Carrington recorded, people are also then able to conclude that this bombardment of the Earth with charged particles was due to that flare that Carrington observed, or was associated with that flare at least. And this is sort of what I mean when I refer to space weather. It is both the electromagnetic radiation that we see in the form of flares, as well as all the particle flux that arises due to or following that flare event. So space weather is both the photons as well as the electrons and protons. It's all of it. So that's space weather then. And I said that flares weren't observed until 1859. That's not because flares weren't occurring. It's because flares historically are really difficult to observe. This is because even though they're quite energetic, they're not as bright as the solar surface, not usually at least. That's why the Carrington event was so extreme. The fact that Carrington was actually able to observe the flare was indicative of just how energetic it was. But normally the sun's brightness gets in the way of us being able to observe flares. That was until we invented coronagraphs, which act very similar to like solar eclipses. It blocks out the light from the sun's disk so that we can see the outer atmosphere called the corona, hence the name coronagraph. And I really love this picture. It has the quintessential flare loop, which I'll talk more about. But this is a picture from the Soho LASCO instrument, just gorgeous. Now, the most energetic flares can produce what are called coronal mass ejection. Those are the things that carry those charged particles that hit the Earth. So here I have a video from the 2003 Halloween solar storm, which I would also recommend people look into. It was, I say it was a cool event. It was also economically devastating because, again, it affected power lines. But here's an example of what these flares look like. So there it is, bursting, sending off its electromagnetic radiation. And then in just a second, you're going to see a bunch of snow on the screen. And I just want to point out this little blob right here. That is Mercury going around the sun. But okay, in just a second, yeah, all that snow. So all of that snow on the detector, that's not photons. Those are the electrons and protons hitting the detector. So thankfully, we don't have to wait for eclipses. And thankfully, we don't have to wait for really extreme events in order to understand what space weather is like from our sun. So that's what space weather looks like on the sun, but I wanted to talk a little bit, take some time to talk about what's actually producing the space weather. It's a rather complicated experience, and so I just wanted to give a small baseline understanding of what's actually happening. So to start, I'm going to go back to that Soho LASCO picture of the coronagraph, and I'm going to zoom in on this little area here, or I say zoom in, I'm going to represent it as this schematic. So in this schematic on the right, that yellow is representing the solar surface. And then all of these lines, these blue lines with those arrows, are the magnetic field of the sun, and it's representing the direction of the magnetic field. So let's maybe compare these two images a little. First off, maybe one of the most prominent features in this image is this really bright blob at the center. And this is actually associated with what's referred to as a hot flare loop. So this is a bunch of really, really hot material, tens of millions of Kelvin in temperature, or tens of millions of Celsius in temperature, that are contained within this really dense, really strong magnetic field. So that's what we're seeing right there. Now, this larger, wispier structure that isn't quite as dense, isn't quite as hot, so it doesn't appear as bright. This is material that's still contained within a magnetic field, but contained within a much larger magnetic field, coronal magnetic field. As you can see, this is huge. That white circle in the coronagraph represents the size of the sun. So this loop is several times larger than the size of the sun, so quite big. I probably should have put a little Earth diagram in for reference, just to give a sense of how much material is being contained in here. So this is all contained within a magnetic field. And in the instance that your flare is energetic enough, then sometimes you can break open those magnetic field lines. And when that happens, then the material is free to escape into interplanetary space. And at that point, that's when you have a coronal mass ejection. So I wanted to just take a couple of minutes to go over the phenomenology a little bit so that you understand that although I talk about photons and particles separately, they're both tied together within the same phenomenon. And I realize I went through quite a bit quite quickly, but really the only thing, or the thing I really hope you take away, is that this is all due to magnetic fields, which is one of the worst things you can tell an astronomer. But magnetic fields are the accelerators responsible for flares and the associated space weather. So that's space weather as we understand it, and more specifically how we understand it on the sun. But what about other stars? So one of the really cool things about magnetic fields is that they can accelerate particles in a lot of different ways, which is great because accelerating particles produce photons. They produce electromagnetic radiation. That's how we observe things in the universe. And because the magnetic field has so many different ways of accelerating these particles, we can actually observe flare-related emission across the entire electromagnetic spectrum. So for instance, in the radio, this is going to be associated, again, with material contained in the magnetic field, as well as shocks that are driven by the magnetic field and by those coronal mass ejections. Microwave wavelengths, so around a centimeter or a millimeter, this is again due to electrons gyrating along the magnetic field. In the visible, like we were seeing in the coronagraph, and like how Richard Carrington observed, this is associated with the solar surface heating due to all of those hot electrons contained within that flare loop. And we even get emission in the X-ray. That's because, again, that flare loop is tens of millions of Kelvin. It's exceptionally energetic. and that's going to be producing the most high energy photons like X-rays. So all of this is to say that flares in space weather, it's a multi-wavelength phenomenon, and we've observed solar activity across all these wavelengths, and we've observed stellar activity across all these wavelengths. So we can pretty well constrain that flares on other stars act like flares on the sun, which is really convenient. The problem, though, is that we can observe all this electromagnetic radiation from the stars, but we can't observe particle flux from them like we can observe from the sun. We can try to put constraints on how much particle flux might be occurring based on some signatures we see in different parts of the electromagnetic spectrum, but there's no way to know for sure that a certain amount of particle flux is actually occurring. So this gets a little bit tricky, but it's also the whole point of my thesis. So, in particular, for my thesis, I have been focusing on the visible part of the spectrum, so around 500 nanometers. That's how we observe. That's I believe, our most sensitive wavelength of light that we can perceive. And I also work at low frequency radio at a few tens of megahertz or a few meters in wavelength. So I'm going to focus on these two parts of the spectrum when talking about how we study space weather from other stars. So for starters, let's talk about the visible light. In order to do this, I have a nice light curve, or this is the brightness variation of the star as a function of time. This light curve is of the star TIC 108.02452, a very memorable name. And this was collected by the Transiting Exoplanet Space or Survey Satellite, or TESS. So this is a TESS light curve for this star. And probably the most prominent feature of this light curve is that the flux, the brightness of the star, is varying periodically. That looks as much like a sine wave as I've ever seen. As it turns out, this variation is due to star spots. So at this point where the brightness of the star is lowest, this is when a lot of the light is being blocked due to star spots. So a lot of star spots are visible at this time. At the point where the brightness is highest, that's going to be corresponding to when the fewest number of star spots are visible. And so because of this periodicity in it, we can then start to conclude that these star spots come into and out of view at a periodic rate. And this periodicity is actually associated with the rotation rate of the star. So how fast it's rotating around. So this would be the period of the star from peak to peak, or similarly trough to trough. As it turns out, this is a rotation period of about 6 days, which, for reference, the sun's rotation period is about 24 to 26 days. So this star is really whipping around. It's rotating 4 times faster than the sun. And not only that, we also happen to know this star's age. Dr. Mark Popenchak gave a webinar a bit ago, also for iTelescope, and he goes over determining stellar ages, so I would recommend checking that out. But I'll just say here that we happen to know that this star is about 100 million years old. So these two pieces of data together sort of start to suggest, oh, sorry, I should clarify that that's 50 times younger than the sun. So then that starts to suggest that younger stars rotate faster than old stars. And I should clarify, I'm making that conclusion for this singular star, but this is a conclusion that is actually drawn from measurements of hundreds, thousands of stars. It just so happens that this star fits that statistic really nicely. So that's rotation. It's not necessarily space weather. In order to talk about space weather, it's helpful to get rid of the variability due to star spots so that we can focus on variability due to things like flares. So let's flatten this out a little bit. And what I hope is obvious here is that there are three really distinct spikes in the brightness of the star. And in order to evaluate this, let's zoom in just a little bit more. So this isn't just a spike, there is some structure. We see that the star gets really bright really quickly and then gradually decreases in brightness over the course of about an hour. And this is actually the quintessential flare light curve. This is what flares look like in the X-ray and in the optical. So great, we've detected a flare. And because we know the brightness of the star and its temperature and its radius, we can then conclude the energy of the flare, how much energy it must be putting out in order for it to appear this bright. And as it turns out, that energy is 10 to the 34 ergs, which I realize that number might not mean a lot, especially since erg is kind of a weird unit anyway. But what's important to know is that this is 100 times more energetic than any flare we've ever observed from the sun. And not only is it more energetic than any flare we've ever observed, but there's 3 of them within the span of a couple of weeks. So this star is not only having very energetic flares, but it's having them fairly frequently. So this together then suggests that younger stars have stronger flares than older stars, and it has them more frequently. And because now we all know that magnetic fields are responsible for flares, we can then sort of conclude that younger stars probably have stronger magnetic fields than old stars. So, I just want to emphasize that this was some code that I developed for a project that I'll be submitting for publication soon. So that light curve plotting and then the flattening and the flare identification and flare energy calculation, all that code will be going up on GitHub soon for anyone to use, because reproducibility is the cornerstone of science. So keep an eye out for that if you're interested in flares. But so altogether, what we learn about stars and young stars in the visible light is that they rotate faster, and by extension, they have stronger magnetic fields, and then by extension of that, they have stronger flares and they flare more frequently. And all this sort of suggests some dire consequences for a young Earth. All this suggests that when the sun was 100 million years old, a few 100 million years old, and when the Earth by extension was only 100 million years old, that the impulsive radiation environment, so the flaring environment of the Earth, was going to be way more extreme. The Earth was probably receiving way more UV flux, way more X-ray flux, ionizing radiation than it receives today, which may be why life exists in the first place, right? All that ionizing radiation drives a lot of really interesting chemistry. So it may be that that extreme environment is responsible for life on Earth, or it may be that life on Earth exists in spite of it. It's an open question we're still trying to figure out, and I'm neither a chemist nor a biologist, so I will leave that as an open question here. So that was what we learned about space weather from stars in the visible light, but now on to the radio. And the radio is quite a beast. Here's an example of all the different radio emission we see from the sun. And there's a lot going on here. There's not enough time in a single day to go over everything that's happening here. But there's just a few things I want to emphasize, namely that when we say radio, that is a really broad term. It spans 4 orders of magnitude. So wavelengths as short as a millimeter or a centimeter, and then wavelengths as long, in this case, meters, but really we see radio emission with wavelengths in the order of kilometers. It is a huge range of wavelengths as compared to the optical, which it only varies by a factor of a few, right? It only goes between about 300 nanometers to 900 nanometers. So radio is quite a broad term, and there's quite a lot of physics happening in the radio because it is so broad. However, when we study other stars, we don't normally look at really low frequencies. Usually we look in this regime right here at gigahertz frequencies or at around centimeter wavelengths. And unfortunately, I don't have a lot of pretty pictures for this part of the spectrum, but I can tell you a bit about the conclusions that we have from gigahertz frequencies. The first is that younger stars have more radio emission. They're more radioluminous. And it turns out the implication of that is that they have stronger stellar winds. So we also have a solar wind. This is just particles that the sun launches off, not due to flares, but because of its ambient quiescent activity. So the fact that the sun is radiating all the time, that pushes particles around, and that produces a solar wind. But the stellar winds on other stars is much stronger. So again, the particle flux at a young Earth might also be stronger. Additionally, this is a result that I'm working on currently, but as you might guess, because stars flare more frequently than they're younger, then younger stars are also going to burst in the radio more frequently. And again, this just feeds into the idea that younger stars are more active, but it's exciting to see it in the radio because the radio is more strongly associated with the motion of particles. So the fact that we see more radio bursts for younger stars might indicate that these stars are having more impulsive particle flux events. Now, at megahertz frequencies, we actually don't really know anything about other sun-like stars. Historically, traditionally, sun-like stars have not been the priority for low frequency radio, so megahertz frequency radio observations. Despite that, there's a lot of really interesting physics happening at megahertz frequencies on the sun. And so I wanted to take some time to go over what that is exactly, because it's really neat and will be really important for understanding space weather. So to talk about this, I'll be showing you some data from the long wavelength array at the Owens Valley Radio Observatory, or I'll also be calling it the OVRO LWA. It looks quite different from an optical or a visible telescope. That is because its wavelengths are so much longer than visible light. But that aside, this is what the sun looks like to the OVRO LWA. I love this picture so much. I think it's just so amazing. There's a lot of physics happening here. This emission is driven by acceleration processes that are very different from the acceleration processes that are responsible for visible light flares or even X-ray flares. So this is a special kind of emission called plasma emission. So this is emission originating from electrons basically acting like a laser. I won't get into the nitty-gritty of that here, but I'm more than happy to talk about it later if folks are interested. So the cool thing about plasma emission, again, is really different from the flare emission we see in the visible. So in the visible, that was originating from that hot material on the surface of the sun or from the surface of the star, which means it was dependent on the temperature of the material that was producing the flare. Plasma emission, on the other hand, what it relies on isn't temperature at all. It depends on the speed of the electrons and then the density of the surrounding material, so the density of the corona. And I'm going to go into a little more detail that I hope makes this make a little more sense. So in order to elaborate on this a little more, I'm going to zoom into this chunk of this plot here. So what I'm actually showing here, this is the intensity of the radio emission as a function of the frequency of the radio, so that's on the y-axis, as well as the time that the emission reaches the Earth, so that's the x-axis. So this is fun. It's a multi-dimensional problem, but let's break it down a little bit. So I'm going to be focusing on this nice sweeping structure right here. So not this other fun structure right here, just this sweeping structure in the middle. So for starters, we see that it starts around right here, around 0.75 hours into the observation. And we can see here also that it's starting at higher frequencies, right? It's starting at around 60 megahertz. As it turns out, for plasma emission, the higher density material that you're moving through, the higher the frequency you observe it at. So this all implies that the electrons are starting at a high density material. Now, towards the end of the observation, we see that we have drifted now to much lower frequencies, which means the electrons are now in a lower density plasma, or lower density part of the corona. So the emission drifts from high to low frequencies, which suggests that the material is moving from a high density region to a low density region, which this suggests that material is moving outward in the corona. Okay, so there's the physical picture. That's what's happening. We're seeing material move out in the corona. As it turns out, because this drift is lasting for about 45 minutes, so because it drifts from such high density to such low density within 45 minutes, we can start to constrain how fast this material is actually moving. And as it turns out, it's moving about 0.3% the speed of light, which is 3 million kilometers per hour. And we have a poll question related to this, Christian, if you want to put it up.
Okay, I'll share now and please comment.
Oh, folks were close. Yeah, so the fastest man-made object is actually moving 690,000, did I say 609? Yeah, 690,000 kilometers per hour, so that third option. This is actually the Parker Solar Probe. So that's a probe that was launched to study the sun, in particular to study the particles of the sun. At its closest approach, it's within, I think, 11 solar radii. Mercury is, I believe, at like 50-ish solar radii. So the Parker Solar Probe is interior to the orbit of Mercury, so quite close to the sun, which is why it's moving so fast. Fastest man-made object is around 700,000 kilometers per hour. This material is moving 3 million kilometers per hour, or about a couple thousand kilometers per second. So it's like if you could go from LA to Salt Lake City in a single second. It's pretty impressive in speed. And this is due to a coronal mass ejection. That is how fast coronal mass ejections can move, quite speedy. You can maybe start to understand why it's such a big deal when they hit the Earth, just because they're moving so fast. Those are quite energetic particles. So this is great. This is the sun at megahertz frequencies. And what this suggests is that if we could observe this on other stars, then that would tell us about the density of the star's corona, which is a really big deal, it turns out. It is really difficult to measure the density, to measure any parameters of stellar corona. We just have very little information about what the atmosphere of other stars are. We know their composition at the surface, but we very rarely know their density or their temperature. So this is great because the plasma emission is intrinsically tied to the plasma density. If we measure plasma emission from another star, we inherently know the plasma density. So, wow, that would be great. The other part is that it tells us whether a coronal mass ejection has occurred on the star, right? Because you need really fast electrons to accelerate that laser process. And it turns out you need something moving at least as fast as a coronal mass ejection in order to do that, which is another big deal because coronal mass ejections are really hard to confirm have occurred on other stars because we can't directly measure the particle flux. But if we see this sort of emission occurring on another star, we can be almost certain that a coronal mass ejection has occurred. And the final thing, which is sort of exciting for me as a PhD student pursuing this for my thesis, is that this emission has never been detected on sun-like stars before. Again, sun-like stars haven't been the priority for low-frequency radio observations. So there's a lot of really cool untapped science to be done by studying stars at megahertz frequencies. So everything all together now between the visible and the radio. We now know that young stars have more flares. We know that they have more energetic flares. We also know that from the radio that they have stronger winds. And additionally, they may have more frequent particle events. That parentheses, that may is really contingent on being able to constrain radio bursts with actual particle motion out of the stellar corona. So it may have more frequent particle events. The way we would want to constrain that is probably through megahertz radio observations. But all this together now really suggests that when life was first forming on the Earth was receiving more UV radiation, right, through the flares, more UV and X-ray radiation impulsively. It was also experiencing more steady particle bombardment. So that steady particle bombardment, that's coming from the winds that we know about that are happening on younger stars, and so was probably happening on the young sun. And then additionally, there may have been possibly more frequent and energetic impulsive particle bombardment. So that impulsive particle bombardment referring to coronal mass ejections. But again, we don't know that. The statistics on stellar coronal mass ejections are wholly unconstrained. And I believe the future towards understanding that really lies in studying these stars at low frequency radio where they've been neglected. And so in order to remedy this, I have been working on instrumentation, as I mentioned at the beginning of the talk, with my optical visible observatory flare scope. And then there's also the long wavelength array at Owens Valley, which I showed that really pretty plot from. So hoping to combine these two. I say hoping, I am currently combining these two. These two instruments are working together to observe the same stars all night, every night. So they are currently collecting a whole lot of data on a few select young sun-like stars. And from this, I hope to start to really build up that picture of coronal mass ejection statistics for young stars. And so then we can maybe start to draw some conclusions about what coronal mass ejections looked like on the sun when it was younger and when life was first forming on the Earth. And an example of what this looks like, so up top, that is the intensity as a function of time and frequency, which I showed for the sun earlier. So that's coming from the overall LWA. Below that, that center panel is if you compressed it down vertically. So this is basically just a light curve. It's just the emission as a function of time. And then below that is the visible light curve from flare scope. So unfortunately, no flares were happening at the time, but this is just to demonstrate that coordinated observations between the radio and optical or radio and visible is doable, including other telescopes, other parts of the electromagnetic spectrum would be even cooler. As I showed earlier in the talk, different parts of the electromagnetic spectrum are going to be seeing different parts of the flaring process. So it'll be super exciting to incorporate more instrumentation in the future. But right now, for those that appreciate instrumentation and photometry, I want to point out that my design decisions were not for naught. They did not go to waste. Flarescope has around a few millimag precision, so sensitive to within a few hundred parts per million change in the flux from sun-like stars on timescales on the order of a few minutes. So it was worth it to have the small field of view so that I could have the sensitivity. And so with that, I'll leave you with some pretty pictures from Flarescope, as well as my favorite star, my cat Snuffkin. And yeah, thank you all.